Today we're going to talk about Monte Carlo methods. It's me, I'm Graham Eversden, and my partner Matt. Monte Carlo methods are named after a gambling hotspot in Monaco, since chance and random outcomes are essential to the Monte Carlo methods. Casinos, a lot of casino games can be modeled using Monte Carlo, and so that's how it got its name. Monte Carlo methods are used to simulate events that are just hard to predict, like poker games and stuff like that. And it's used to understand uncertainty and predictions. How to use them? You model the situation you want to study, and then you define what's like a successful trial, and then you run a lot of trials, and then you put successful trials over total trials, and that equals the probability of the event occurring. For March Madness, that's our first example.
At midcourt, extra pass. And it goes for the win! The three-pointer by
We can use Monte Carlo methods to simulate the chance of getting a perfect March Madness bracket. If we assume every team has a 50% chance of winning each game, then we can run the following code to determine the probability of a perfect bracket. And that code is here. We have March Madness.
Pulling it down, getting around Zubac. At midcourt, launches the shot. Oh, almost went in. And Duke is the king of the dance, 2010.
So here's our code. So we start out, we create a function called March Madness, and the winners, it's just an empty list. And for I in range 0 to 126, that's because there are 126 teams. Well, there's 63 games, and then each game has 2 teams, so that means there's 126 teams. And you go by 2 because there's 2 teams per game. The victor is a random choice, either Team A wins or Team B wins. If the victor is Team A, then you add the number of team to the list, and if the winner was Team B, then you add the number of Team B to the list, and then that's what you return. And then for the real tournament, this is what the actual results were of the tournament. You just run that and you get the actual results. And then trial succeeds, the bracket equals March Madness, and then if the real tournament does not equal the bracket, then if false, obviously the trial did not succeed. And if that's not true, obviously then the real tournament does equal the bracket, and we return true. And for the odds of a perfect bracket, you set trials equal to 100 to start. And for successes, it starts at 0, and then you loop through each trial. And if the trial succeeds, is true, then you add 1 to the successes, and then you return the probability, which is just successes over trials. And here's your answer, and this is just to make it look nice at the end. So I'm going to run this. And with 100 trials, we actually got 0.0 because the odds of getting a perfect bracket are so small that you're just not going to get, even with 1,000 trials, you're not going to get the right answer because the odds of getting a perfect bracket are 1 over a couple billion. And that's how you apply Monte Carlo methods to March Madness.
Freshman on him, gets past him in the paint. Carter floats it and one. Terrific clock awareness.
DiVincenzo through. There's time here for Stokes. Maybe not for that. McGurl got it away in time. Yes! Oh, goodness. My goodness. 3 seconds, 2 seconds. McQuaid blocked by Moyer. Throws it up. Oh!
All right, so another thing we're going to talk about using Monte Carlo methods is the birthday problem. So that's just the question of if you have a group of people, what is the probability of any 2 of those people having the same birthday? So it's a pretty simple problem to model. So we're going to go over to Paizo. And so this is some code that we got online. We have it cited here. So basically we have the function birthday problem, and it's taking class size, which is just the number of people in the group, and then the number of trials is just the number of trials you want to run. So first we have here dupe count equals 0. So that's what's gonna track. That's the variable that's gonna track how many duplicates you have over all the trials you have. So this first for loop here essentially it's just giving us a list of it's giving however many trials we have, it's going to be that many lists of numbers, and it's just the list is just going to represent people's birthdays. So it's just a random number from 1 to 365, each representing a different birthday. So once the function generates those lists for all the trials, then it's going to go through each list and figure out which of those lists has a duplicate. And so essentially, so found dupe is set to false, but once going through the list, once this for loop catches a number that's in the list more than once, then it's going to set found dupe to true. And then every time that found dupe sets to true, then the count for the duplicate is going to increase by 1, because see here we're still within the same for loop up top. So once it generates the duplicate count out of all the trials, then essentially it just puts that over the number of trials to give you the probability. So here we're going to run, we have class size of 23 and 1,000 trials. And it says the probability of a shared birthday in a class of 23 is 0.508. And then I'm going to increase this to 366 kids in a class, and we'll run it, and it's taking a minute, but it says it's a probability of 1, so it's a 100% chance. So that's surprising, but that just shows the power of Monte Carlo, because it can show you maybe some results in probability that are hard to imagine. You can also see that the probability kind of goes up pretty quickly with numbers. So I'll try 30 right now. And it's already the probability of 72%. I'll go to 50, and we're already at about 97%.
So the March Madness example highlighted one of the limitations of Monte Carlo. For like very low probability events, there's just not enough time to run like enough trials to produce like a solid probability. Because it's so hard to get a perfect bracket, we would have had to run like a couple billion trials probably until we actually got something that equaled a perfect bracket, which means it would take basically forever. Those type of problems are called intractable, where you don't have enough time to actually complete the problem, even though it is possible using a computer. Another limitation of Monte Carlo methods are that they can't be used to simulate the probability when the rules of the situation aren't clear. For example, we knew exactly that there were going to be 63 games in the tournament, or like if you're trying to mimic a poker game, you know that there's like 52 cards in the deck and 4 aces, and so if you're trying to get the 4 aces, you know like exactly, you can figure out like the probability. If you don't know like the exact parameters of your situation, you're just not able to use Monte Carlo methods.